Hello and welcome back to the AICE Chemistry lecture series. Today we are going to go over pi bonding and sigma bonding as well as hybridization for chapter 4, section 5. So in this section we're going to take a look at how bonding occurs and what happens to the orbitals as the atoms bond. Some of this is going to be things that we saw at a very basic level last year, and then some of it will be brand new. We're going to start with hybridization because in order to create bonds, atomic orbitals have to combine in order to make what we call hybrid orbitals. Essentially, the reason for this is that atomic orbitals are not very well suited for bonding. If we think about the shapes of the orbitals. So we have from last year the atomic orbitals. Are S, which is spherical in shape, P, which is an hourglass or a dumbbell shaped orbital, D, which is for the most part a clover shaped orbital, although there are other shapes like the one with a ring, and then F, which is too complex to draw, but it's essentially just a double d orbital with some of those coming out towards you and behind you, and then some of them coming out to the side as well. But we're not going to talk too much about the F orbitals since it does not participate in bonding. The ones we want to focus on are going to be the sp orbitals and a little bit on the d orbital, which participates in expanded octets. The atomic orbitals do not directly participate in bonding. Electrons are found in the atomic orbitals, and therefore they have to participate in bonding, but not directly. Why? Imagine we had an s orbital, a p orbital, another p orbital, and then another p orbital, because we have a bunch of electrons in an atom. How is this amalgam of shapes supposed to form something like a tetrahedral for carbon? I'll draw this in 3 dimensions. So imagine we have something as simple as methane, which is tetrahedral in shape. How are we supposed to form these bonds with this combination of s and p orbitals? It's not very likely to happen. This cannot occur because if the carbon atom here at the center, we can't arrange these orbitals into this conformation. So what happens during bonding is that those atomic orbitals actually don't directly participate in bonding. They combine to form what we call hybrid orbitals. Hybrid orbitals are easier to arrange around the atom, and they all look the same. They all look like a p orbital with a very small side on one side and a very large lobe on the other. The number of p hybrid orbitals that we're going to form is going to be equivalent to the number of atomic orbitals that combine to form them. So essentially, an s and a p atomic orbital, can combine to form 2 hybrid orbitals. An s and 2 p orbitals can combine to form 3 hybrid orbitals. An s and 4 p or 3 p orbitals can form 4 hybrid orbitals, so on and so forth. All hybrid orbitals look the same. So let's look back at this drawing. So this we said can't happen because we cannot arrange these orbitals into this shape. So let's see what actually happens. When we grab these atomic orbitals, like we said, the s and the p orbital, for example, if we combine an s and a p orbital together, we'll get what we call a hybrid sp orbital. So these are the atomic orbitals. These are the hybrid orbitals. I meant to change the color there. So if we combine one s orbital and one p orbital, that's a total of 2 atomic orbitals, they will create 2 sp hybrid orbitals. What does that look like? Well, if we combine an s, which is a spherical orbital, and a p orbital, which is dumbbell shaped, because we're combining two orbitals, when these come together to form the hybrid orbital, we'll get two hybrid orbitals, which are sp orbitals. So we'll get two of these orbitals that kind of look like a p orbital, but they have a big lobe and a little lobe. A big lobe and a little lobe. So these are both sp hybrid orbitals, whereas the ones that we use to combine them are an s and a p atomic orbital. Now, why does this happen? This happens in order to create molecules that will have the proper shape, because a sphere and a dumbbell cannot properly come together. sp orbitals are very common, as we saw in the slide. sp orbitals are very common for linear geometries. So if we have something like, well, I won't go into specifics yet, but if we can combine these two into a linear geography, essentially what we do is that we put each of these big lobes on opposite sides. So we have the big lobe and the little lobe, and then we have the other hybrid orbital. We put the big lobe and the little lobe, and we can form a linear molecule with an sp, with the two sp hybrid orbitals, which we wouldn't be able to do by combining these two atomic orbitals. So anytime you have a linear molecule, that central atom is going to hybridize to form these sp hybrid orbitals that can then come together in the molecule to create a linear shape. If we added another orbital, so instead of having one s and one p orbital, if we added we'll come over here, we'll add another p orbital. So if we're combining an s and two p orbitals of the atomic orbitals. Then because we're combining three atomic orbitals, what we will get will be three hybrid orbitals, which are called sp2 hybrid orbitals. The 2 tells us that there are two p orbitals being combined. So essentially what we will be combining here is an s, a p, and another p orbital, which have dumbbell shapes. And these will come together to combine and form three different hybrid orbitals. Again, why 3? Because we're combining 3 atomic orbitals, and they're sp2 hybrid orbitals. Now, it doesn't matter whether they're sp or sp2, all hybrid orbitals look the same. They're all a p orbital, essentially with a big lobe and a little lobe. So we will form 3 of these hybrid orbitals, which again, we call these the sp2 hybrid orbitals because they're made from 1s and 2p orbitals. These sp2 hybrid orbitals can again combine in that central atom to make another shape. sp2 hybrid orbitals are common in trigonal planar. Oops. They're common in trigonal planar molecules, so we're actually going to put this to the side over here. So these 3 will arrange themselves and combine into a trigonal planar shape. Again, the shape of the hybrid orbitals is why they're created. To form a trigonal planar shape out of these 3 atomic orbitals will be too difficult. But now that we have 3 hybrid orbitals, by mixing these together and recreating them, we can easily put one hybrid orbital at the top, one coming out towards the left, and one coming out towards the right, which gives us that trigonal planar shape. So anytime you have a trigonal planar molecule, such as BF3, any trigonal planar molecule will have those bonds created from hybrid orbitals that the boron, in this case, or whatever the central atom is, created. So any trigonal planar shape will have sp2 hybridization because that's what's needed to create those shapes. Now, if we add a third p orbital to this mix, erase this real quick. If we add a third p orbital to this mix, then we are going to create not 2, but not 3, but 4 different hybrid orbitals. So if we have a combination of an s and 3 different p orbitals, p atomic orbitals in an atom, so one circular or one spherical plus one dumbbell plus a second dumbbell plus a third dumbbell, that's going to create 4 orbitals, 4 hybrid orbitals, because we are looking at combination of 4 atomic orbitals, and those are going to be called sp3 orbitals. Why 3? Because they're made out of a combination of 1 sulfur or 1 s orbital and 3 p orbitals, 4 in total. So when we combine these, when we grab these 4, mix them together, and recreate them into hybrid orbitals, again, those hybrid orbitals are going to have the same shape as every hybrid orbital, which is our big lobe, little lobe. So they're very similar to the p orbitals, but with a big lobe and then a little one. The big lobe being where the bond happens. These are going to be 4 sp3 orbitals. Now, why would a molecule, an atom, a central atom create 3 or sp3 orbitals? They create sp3 orbitals because they need to combine into a tetrahedral shape. Now, these 4 can come together in combination to form a tetrahedral, because one can be coming out towards the top, one can be coming out towards the side, one can be coming out towards us, and I'm going to shade that one in to make it 3-dimensional. And then one can be going back to form that tetrahedral shape. So, for example, when we have methane, CH4, that CH4, the carbon at the center, has combined its s orbital, its valence s orbital, with its 3 valence p orbitals to create 4 sp3 hybrid orbitals. And those can then rearrange themselves into 3 dimensions, into a tetrahedral shape, something that the s and 3p orbitals cannot accomplish by themselves. Now, the sp through sp3 hybrid orbitals are used in our common molecules. But if we have expanded octets bring in that d sublevel. That's why only elements in period 3 and above can form expanded octets. So, going back to this, if we're now bringing our expanded octets, we can create even further hybrid orbitals. By combining, now I'm going to erase this. So by combining not just the s and the 3p orbitals, by combining the s, the 3p orbitals, and bringing in an additional d orbital, we can make 1, 2, 3, 4, 5 atomic orbitals being combined. So we make 5 hybrid orbitals. Oops. So we're going to make 5 hybrid orbitals, and these are going to be called sp3d orbitals. The d now symbolizing that d sublevel, or that the orbital that we have brought in. So that's a combination of the s orbital, which is a spherical, 3p orbitals, which are all dumbbell shaped, and now also a d orbital, which is clover shaped. When all 5 of these combine and they mix together, they create 5 hybrid orbitals. Again, hybrid orbitals always have the same shape, so it's still going to be that big lobe, little lobe, big lobe, little lobe, big lobe, little lobe, big lobe, little lobe. And then same thing here. And these are going to be 5 sp3d hybrid orbitals. These again are created because we can form the shape that requires 5 bonds much more easily by using this. Which shape requires 5 bonds? It requires an expanded octet, and that will be the trigonal bipyramidal shape. So something like PF5 will have this, or PCl5, if you remember. It's P with the two chlorines, one top and bottom. The chlorine here, and then one chlorine coming out towards the back and one chlorine coming out towards the front here. And that's our trigonal bipyramidal shape. How do these five things can never create that shape, but these five hybrid orbitals can easily combine to create that shape, because one can go up with its little lobe in the middle, one can go down with its little lobe in the middle, one can go towards the right with a little lobe, one can go back behind with its little lobe in the middle, and then one can come out towards us with that little lobe stick in the middle of the atom. And this can create that trigonal bipyramidal shape. That's why hybrid orbitals are made every time. Lastly, we have one more shape we haven't discussed, which is whenever we have a 6-bonded central atom, which is going to again require an expanded octet. So we're going to go ahead and erase this. So if we have now not one d orbital added to the s and the p orbitals, but two d orbitals added here, now we have 1, 2, 3, 4, 5, 6 different atomic orbitals being combined. Those 6 atomic orbitals will create 6 hybrid orbitals, which we're going to call sp3d2 orbitals. Again, s meaning one s orbital is being added, 3 p's, so p3, 2 d's, d2. So this will now bring in an extra, let's move this over here. It will bring in an extra d orbital into the mix, so another clover-shaped orbital. These 6 atomic orbitals cannot form any shape because that will be too convoluted, but when they combine, they can form their hybrid orbitals, which all have the same shape, big lobe, little lobe, and it's going to combine to create, that's a little too much, it's going to combine to create 6 of these hybrid orbitals. 4, 5, and then 6. These 6 sp3d2 orbitals can much more easily come together to form the required shape. Something that those atomic orbitals could not do because of their complex shapes. So these can come together in a different manner to create what we call an octahedral shape. The last one of the expanded octets that we talked about in the last section. So something like SF6 will have this shape. So S with the fluorine, and then we had a fluorine coming back, a fluorine going back on the other side. So essentially forming a square in the middle with fluorines. This octahedral shape cannot be formed by our atomic orbitals, but our sp3d2 hybrid orbitals can easily form this shape because, again, we have the big lobe and the little one, which doesn't really obstruct anything. We have the same going down. We have one that goes back on the left and one that goes back on the right. And then we have the ones that come out away from the screen or from the plane, forming those 6 orbitals. So we have 1, 2, 3, 4, 5, 6 hybrid orbitals come together in this shape so that the molecule, the sulfur, can bond in this way, in this structure. So those are our different hybrid orbitals and what they form. Now, do keep in mind that some atomic orbitals can hold, or some hybrid orbitals can hold lone pairs of electrons as opposed to being bonded to atoms. We'll talk about this, but any of these fluorines could be replaced with a lone pair of electrons, and that hybrid orbital will still exist. It will just hold the lone pairs of electrons instead of holding the bonding electrons. Because orbitals, and especially hybrid orbitals, can do either or. They can hold bonding electrons or lone pairs of electrons. So get rid of this and go back to the PowerPoint. Oops. So we can see here that this chart shows us which shapes form which hybrid orbitals. If we have something that has a linear structure, it forms sp hybrid orbitals, so that we can have that linear structure with an s and a p sublevel. Triangular planar or trigonal planar are going to form by sp2 orbitals by combining s and 2p orbitals to form this 120 degree shapes. Each one of these lobes, by the way, is an orbital, not the whole thing. So this is just showing you that there's three, but only one of these lobes is that orbital. sp3 is formed by tetrahedrals, sp3d by trigonal bipyramidals, and sp3d2 by octahedrals. Also, again, remember, these could be, instead of bonds, lone pairs. So, for example, if we had this sp3d shape, but we filled two of these with lone pairs of electrons. Oops. And then these two will go to something like a hydrogen from an oxygen in the middle. That will be water. That will be a bent structure. Tetrahedral is the shape of the orbitals, the orbital geometry, not the geometry of the atom, of the molecule itself necessarily. So a molecule that is bent like water could be formed from sp3 hybrid orbitals. Moving on. So molecular orbitals, when covalent bonds form, they are formed by the combination of either hybrid or atomic orbitals that overlap with each other and then bond or meld together to form a molecular orbital. So, for example, in a very, very simple, straightforward example, if we have a hydrogen and a hydrogen trying to bond with each other, those hydrogens consist of just an s orbital. Now, hydrogens don't undergo hybridization because hydrogen's whole electron configuration is 1s1. There's no other atoms, no other orbitals for the s orbital to hybridize with. So we have the hydrogen with its 1s orbital, the hydrogen with the other s orbital. When hydrogens go to bond and form that bond between the hydrogen atoms, their orbitals meld together. They mesh together to form what we call the molecular orbital, and those electrons are now found in that molecular orbital. So this is the atomic orbitals. The atomic orbitals then, which are the s orbitals, overlap with each other, which is where those electrons are going to be shared. Let me put that in a different color. So they overlap with each other where those electrons are going to be shared, because those electrons were originally just in their s orbitals. Once they overlap, they actually fuse together to form the molecular orbital, which this is where the electrons now live. The greater this overlap is, the stronger this molecular orbital becomes. Now, there are two kinds of molecular orbitals. There's sigma and pi orbitals, or what we call sigma and pi bonding. So let's look at what the different situations of this can be. But keep in mind, molecular orbitals are created when either atomic orbitals or hybrid orbitals overlap with each other to form a bond and then fuse together to create a molecular orbital. So moving forward, so there are two types of molecular orbitals or molecular bonds. There's sigma and pi bonds, and we're going to look at these now. Let's start with sigma. Sigma orbitals or sigma bonds, we'll call a bond that forms a sigma orbital, a sigma bond, happen when orbitals end up lining up end to end or overlapping end to end to form a bond. we call them a sigma bond, and these are the stronger of the two types of covalent bonds because they have more overlap. This can happen between any combination of hybrid or atomic orbitals. Now, we already saw one that happens in only one atom, which is the overlap of two s orbitals to form a sigma bond. We saw that with hydrogen. That only happens in H2 because H2 is the only molecule where the atoms only have the s orbital and there's no hybridization. That's unique to hydrogen. Usually sigma bonding happens either between this hybrid orbital of the central atom and the s orbital of a hydrogen that's bonded to it, or the sigma or hybrid orbital, of two different atoms that are bonding. So carbon to carbon, for example, or carbon to oxygen. Every single bond in a molecule is made from sigma bonding. All multiple bonds have only one sigma orbital, and we'll talk about why in a little bit. But essentially, this is going to happen anytime two molecules or two atoms are trying to bond. So, for example, excluding the rest of the molecule, imagine you have a carbon in a central atom, something like methane, CHHH. If we focus in on just one of these bonds, the carbon-hydrogen bond, the carbon in the center, before it goes to bond, it's going to create these hybrid orbitals that we discussed, because the s and the p orbitals alone could not form an appropriate bond. So that carbon now has four atomic orbitals, or four hybrid orbitals pointing in different directions. We'll look at one. And then the hydrogen on the other side only has an s orbital because hydrogen does not undergo hybridization. So the hybrid orbital from the carbon and the s orbital from oxygen are going to overlap. So we're going to get that hybrid orbital from the carbon overlapping end to end with the s orbital from the oxygen, with the electrons being shared in between. Let me use a different color. The electrons being shared in between those orbitals. This is the first step to bonding. Well, technically, the first step to bonding is the hybrid orbital coming together, but the hybrid orbital overlapping with the s orbital, the carbon hybrid orbital overlapping with the hydrogen s orbital are going to overlap. The electrons are going to be in the shared space in between. Once they overlap, they're then going to create what we call the molecular sigma bond or the molecular sigma orbital. Essentially, that area where the hybrid orbital and the s orbital are overlapping is going to merge together into an orbital. Now, the little tail from the hybrid orbital is still there. So you see we have this tail still there. And then these two merge together to create this bigger structure. These electrons, these bonding electrons, can be anywhere in this pi molecular orbital. Sigma bond or sigma molecular orbital. The same thing can happen if two carbons are bonded to each other and they both have hybrid orbitals. So not only can hybrid orbitals overlap end-to-end with s orbitals, and s orbitals overlap end-to-end with s orbitals like we saw earlier, but two hybrid orbitals can also overlap. So if we think of something like ethane, C single bond C, and then we have those three hydrogens sticking out of each carbon, this is a bigger, more complex molecule, but it serves the purpose here. If we look at this ethane and we focus in on this carbon-carbon single bond, that's what we're looking at here. Each of those carbons will have hybrid orbitals that it has created, and then those hybrid orbitals can overlap end to end to create a bond. So end to end. Oops, let me draw that a little better. So when they overlap end to end, again, the electrons are in this shared space in the middle, but this is not going to stay as an overlap. These two areas that are overlapping are going to end up fusing together and creating our sigma bond but this sigma bond is between atomic orbitals. So notice how we have that tail on either side with that shared area in the middle, which is the molecular orbitals, the whole thing. These electrons are going to live in this area here, wherever they seem fit. They're moving around. But notice how even though both of these are sigma bonds, they look different. Why? This is a sigma bond created between a hybrid and an s orbital. This is a sigma bond created between two hybrid orbitals. And that's even different from, if we go back, the sigma bond created between two s orbitals, which neither side has a tail. So be very careful when you're asked about these on the AS exam, which you will be, asked to draw them, whether they're asking you to draw the molecular orbital created between a hybrid and an s orbital, which will look like this, the molecular orbital created between two hybrid orbitals, which will look like this, or the molecular orbital created between two s orbitals overlapping end to end, which will look like this. Not only that, you could also be asked to draw the overlap of the orbitals that leads to the sigma bond. And in this case, you will draw what I have drawn here. Not the fully formed molecular orbital, but the two atomic and hybrid orbitals, whichever one version it is, overlapping with each other but not fused together. So be very careful, because the questions draw the molecular orbital, which will be this at the end, is different than show the overlap of the orbitals, which will be here in the middle, versus show the two orbitals that will eventually form the molecular orbital, which will just be drawing the hybrid and the s orbital, or the two hybrids, or the two s orbitals, depending on what you're looking at. So just to recap, sigma bonds happen specifically when we have end-to-end overlap. So this end-to-end overlap only, it will form sigma bonds or sigma orbitals, depending on what the question structure is. And this is going to happen between either atomic orbitals or hybrid orbitals, or just hybrid orbitals, or just s orbitals. And every single bond you see in a molecule is always made out of this sigma bond. If you have multiple bonds, one of those multiple bonds, so if it's a double bond, one of the two, if it's a triple bond, one of the three, will be a sigma bond. So this is giving you a better understanding of what a bond actually is. Not just the fact that it connects two atoms, but what happens to the orbitals when those bonds are created. Now, pi orbitals or pi bonds are different. Pi orbitals or pi bonds are going to specifically happen when orbitals overlap sideways. Now, this is very unique, and it only happens in one situation. But again, pi orbitals or pi bonds are going to happen when overlap sideways of orbitals, and this only happens between p orbitals. Not sp, not sp2, not sp3, not hybrid orbitals, just regular p orbitals, p atomic orbitals. When are these p atomic orbitals going to do this? They're going to do it every time we have either a double or a triple bond. When we have a double or a triple bond, we said that one of those bonds is going to be sigma. Well, the other bonds, whether it's the one other bond in double or the two other bonds in triple, are going to be pi bonds. So in a double bond, we have, and we'll write it up here, in a double bond, a single bond, let me make that smaller. In a single bond, we have just one sigma bond. In a double bond, we have one sigma bond and one pi bond. And in a triple bond, we have one sigma bond and two pi bonds. Now, why does this happen? This happens because of the structure of the bonds. A sigma bond has to happen between the nuclei of the atoms, meaning that you can only form one sigma bond between two atoms. Essentially, if you have two nuclei, there's only one straight line you can form between those two nuclei. So how will you form in multiple bonds? You can put multiple lines on top of each other. You can put multiple pi or sigma pi bonds on top of each other, sigma bonds on top of each other. So what do? We need to utilize the space above and below this bond, as well as the space in front and behind the bond. How do we do that? Well, pi or p orbitals, when they pi bond, can do it very lightly, or they can overlap very lightly. They do this by overlapping sideways. When we have two p orbitals on atoms that are next to each other, those p orbitals can overlap side to side, meaning only a small area of their sides of the p orbitals are actually overlapping with each other. Those can then fuse together to form the molecular orbital, which will normally show like this, as two areas, one above and one below the nuclei, or what we call the line of bonding, or the bonding line. This is one pi bond. So even though you have two different lobes, this is a singular pi bond. The same way we have two lobes to a p orbital, we have two lobes to a pi bond. This allows us to have a sigma bond in between the two atoms, so maybe two hybrid orbitals bonded together, while still having that pi bond above and below. And it actually allows us to put even a second pi bond, if we wanted to, behind and in front of that, of those nuclei. All right, so this is our pi bond that's created. We'll look in a second at how this all comes together in a molecule. But this can only be formed with p orbitals. Now, you might be asking yourself, how can we have p orbitals by themselves? Well, remember that some structures don't use all of the pi or the p orbitals. For example, when we hybridize an s and two p orbitals to create three sp2 orbitals, what you have to realize is that an atom has a total of 3 p orbitals, meaning that one of those p orbitals stayed a p orbital. So any molecule that has sp2 hybridization has a p orbital that hasn't been used. The same is true of sp hybridization. If we, and we'll make this a little more clear here. So if we have s and p atomic orbitals coming together to form the hybrid orbitals, that's going to form two sp hybrid orbitals, like we discussed earlier. If we have an s and two p's, that is going to create three sp2 orbitals. Well, in both of these cases, we're going to have leftovers. Why? When we're talking about the atom, and we're realistically speaking, when we're talking about any atom here, that atom in the valence shell has an s and 3p orbitals. That's always going to be the case. If we have an s and 3p orbitals, and we only use one of them to create our hybrid orbitals, then that means that in this atom we have 2p orbitals left over. If we use 2p orbitals to make hybrid sp2 orbitals, then we're going to have one p orbital left over. Those p orbitals can be used to create multiple bonds. And that's what we're going to look at now. How are these used to create those multiple bonds? Because the hybrid orbitals are what creates our single bonds, or our sigma bonds in a multiple bond. But the p orbitals that are left over are still important because they're going to be used to create double and triple bonds, the pi orbitals, or the pi bonds in double and triple bonds. So let's look at those. For example, any single bond is going to be made out of a sigma bond. So if we have something like this, ethane, where we have carbon with a 4 bonds because we have a tetrahedral here, and then bonded to another carbon that has 4 bonds, or a tetrahedral. Every one of these bonds is created from the overlap of either 2 hybrid orbitals or a hybrid and an s orbital. The carbon here has 1 hybrid orbital, 2 hybrid orbitals, 3 and 4. Like I said, this is a tetrahedral shape, meaning this has 4 sp3 orbitals. The hydrogens, because they don't hybridize, have an s orbital. So these sigma bonds we see right here are all made out of the overlap of that sp3 hybrid orbital from carbon with the s orbital from hydrogen. The only one that's different here is going to be this middle bond. That middle bond, because this carbon hybridized again, because this carbon is tetrahedral in shape, because it has 4 bonds, this is going to create, again, sp3 bonds. So all this carbon has 4 sp3 hybrid orbitals. And again, those hydrogens on the side are going to have those s orbitals. But this middle bond is a bond made out of 2 sp3 hybrid orbitals. So this bond right here is created by 2 sp3 hybrid orbitals overlapping with each other. All of these are sigma bonds because they all come from the direct overlap of either 2 hybrid orbitals or a hybrid and an s orbital. But what happens when we have something like this, a double bond? So let's turn our attention now down here. Here we have carbon that have 3 bonds, 1 double, 2 singles, meaning that these carbons are trigonoplanar. Like we said, because these carbons are trigonoplanar, they have sp2 hybridization, meaning this carbon has an sp2 hybrid orbital here, an sp2 hybrid orbital here, an sp2 hybrid orbital here. So 3 sp2 hybrid orbitals. The hydrogens have, again, just s orbitals. So this bond, the red bonds right here, the red bonds right here, are made out of the overlap of an s orbital with an sp2 orbital. The middle bond right here, because both of these carbons have sp2 hybridization, is going to be made out of the sp2 hybrid orbitals overlapping. So this right here is an sp2. Oh, let me put that somewhere else. So this right here is going to be made of an sp2 hybrid orbital overlapping with an sp2 hybrid orbital, because both of those carbons have sp2 hybrid orbitals. But this is a double bond. That sp2 hybrid orbital overlap only accounts for the sigma bond that is created. But what about that second bond on the double bond? Well, that second bond on the double bond comes from the fact that both of these carbons, because they're sp2 hybridized, means that they also have a p orbital, because we didn't use all 3 p orbitals here, meaning this carbon has a p orbital, this carbon has a p orbital as well. Well, if we focus in on just the p orbitals, which we're doing here, we have that p orbital, and this is 1 p orbital, this is another p orbital. Those p orbitals are going to overlap side to side, creating a pi bond, which is what this green bond is right here, and that pi bond is made from the overlap of a p orbital with a p orbital from each carbon. That pi bond, that p orbital, the p orbital overlap, that's what the second bond is on our CH2. So we go back and we actually uncover this molecule right here. This trigonoplanar carbons form this CH2 molecule, where these carbons are double bonded. That double bond, one of them is a sigma bond. Oh, not a 6, a sigma. It's really hard to draw sometimes. And then the other one is going to be that pi bond created from the p orbitals overlapping side to side. All right. So that's how this whole molecule is created. So these right here in yellow, I want to go over this again. These right here in yellow, this sigma bond, this sigma bond, this sigma bond, and this sigma bond between the carbon and the hydrogen. So these yellow bonds are going to be made from the overlap of the s orbital with the sp2 hybrid orbital, the s orbital from hydrogen, the sp2 hybrid orbital from carbon. This pink bond in the center, this sigma bond, is going to be created, which is one of these two double bonds, is going to be created from the overlap of the sp2 with the sp2 hybrid orbitals from the carbons. And then the one in green here, the one in green here is going to be the pi bond that's created from the p orbital in one carbon overlapping with the p orbital in the other carbon. This is both the p orbital or the p bond, but they're not two individual p bonds. The whole thing, both of these wedges are one pi bond. So that's a pi bond, that's a sigma bond, and these are sigma bonds, but they're created from different overlaps. The CH sigma bond is created from the sp2 overlap in the carbon to the S overlap in the hydrogen, or atomic orbital in the hydrogen. The middle S sigma bond is going to be created from sp2 overlap between the carbons for the hybrid orbitals. And then that second bond in the double bond, the pi bond, is created from the pp overlap. We can also create a triple bond, which we're not going to show too much here because it can be very hard to visualize. But if we add carbon-carbon triple bond in this molecule, C triple bond CHH, then again, these will just be the sigma bonds. This is a nitrogen. So these will be just the sigma bonds right here, created between the S orbital on hydrogen and the sp orbital in carbon. Now, why is this an sp orbital? Remember, it all comes down to shape. This is linear. Because this is linear, that means that that carbon is sp hybridized. Sp hybridization means that this right here is going to have two p orbitals left over. And that's what these are. We have one p orbital here, one p orbital here. Those can cross or overlap with the p orbitals on nitrogen to create two pi bonds. And that's why in a triple bond, there are two pi bonds. And we'll label the top one and the bottom one as pi bonds. With that central one still being a sigma bond. And that sigma bond is formed between the sp orbitals in the carbon with the sp orbitals in the nitrogen. Okay, how do we know nitrogen is sp hybridized? Because it's in a linear molecule. All right. So that's going to be an sp with an sp overlap. This is an sp with an s overlap. And then these are the pi bonds, which, as we know, are made from p to p overlaps. But there are two pi bonds here because there are two p orbitals left over in carbon, since it's only sp hybridized. So this is a type of question you might be asked on the AS exam about hybridization and pi and sigma bonds. The double bond between two carbon atoms, so it's usually helpful to write this out. So we have double bond between two carbon atoms in an ethene molecule, which you don't know what ethene is yet. Once we do organic, you will. But ethene is carbon-carbon hydrogens on each carbon. Consists of one pi bond and one sigma bond. So they're telling us, they're nice enough to tell us that this double bond on the carbon-carbon double bond, there's going to have one sigma and one pi bond. So we have one sigma, and again, I have to keep looking like sixes, and one pi bond. The question is, which orbitals overlap to form each of these bonds? Well, when we're looking at this, we're essentially being asked is to figure out what the hybridization is on each of these carbons. And because the carbons are identical, if you look at them, carbon, single, single, double bond, carbon, single, single, double bond. These carbons are identical. So we could really, realistically speaking, understand that these are going to be the exact same hybridization. Because I have three connections, 2 hydrogens, 1 carbon, this carbon is sp2 hybridized because that carbon is trigonal planar in shape. And this actually corresponds to both of these carbons because these carbons are going to have the same shape, the same everything. Now, if we look at our answer choices, automatically we should be able to cancel out 2 of these. We learned that pi bonds, there's only one option for pi bonds. Pi bonds can only ever happen when a p orbital overlaps with a p orbital. That means that option B and option D are not possible since they have hybrid orbitals overlapping for that pi bond. And we're left with just 2 options, A and C. Well, if we have A and C here, well, all we have to do is figure out what the hybridization of the carbons are, and that's an sp2 hybridization, meaning that sigma bond is going to be the result of sp2 to sp2 overlap, since those are the hybrid orbitals in this carbon. Meaning that the answer is not C, the answer will be A. Another thing that you have to be careful is which bonds are they talking about, because they are saying which orbital overlaps to form each of these bonds. And they're referring to the double bond between the 2 carbons. Had they been referring to the single bond between carbon and hydrogen, then there will be only 1 sigma bond there, and the overlap will be sp2 with an S, because hydrogen, like we said, does not hybridize. So be very careful which bonds are they asking you about, and then being able to look at an atom and figure out its hybridization based on its shape. All right. Let's do one more problem here. And I'm actually going to show you the answer right away. I'll try not to answer the question right away. Sketch a diagram to show how 2 of the sp hybrid orbitals can form a sigma bond. So we're going to be careful with how this question is written, because some questions will ask you about the, and I'm going to write it here on the side, some questions will ask you about the orbital overlap. Some questions will ask you about the molecular orbital that's formed. / bond, because sometimes they call it bond, sometimes they call it orbital. These being the pi and sigma bonds. And some questions will ask you about a process. So if we read this question carefully, it says sketch, so that's first thing we need to know is that we're drawing a diagram to show how 2 hybrid orbitals can form a sigma bond. Not show a sketch of the orbital overlap between 2 sp hybrid orbitals, not show a sketch of the molecular orbital formed by the sp hybrid orbitals, but show a sketch of how they can come together to form a sigma bond. Meaning this is talking about a process, which means it's going to have more than 1 step. And that makes sense. If we look at the marks here, this is a 2-mark question. So this process is going to have 2 parts to it. One will be the overlap, which atomic orbitals or hybrid orbitals are overlapping, and one on the second step being the molecular orbital. Some questions will ask you about just one of these steps, some questions will ask you to draw the whole process. So here we're told that we have 2 sp hybrid orbitals. So which type of hybrid orbital it is doesn't really matter because they all look the same. We have our big lobe with a little tiny one. And if they're going to overlap, what we're going to have is another hybrid orbital, which we'll just draw pointing in the opposite direction. I'm trying to draw it just as big. Pointing in the opposite direction. These 2 are going to come together to overlap. So I'm going to show my overlap. I'm going to show my sp hybrid orbitals. I'm going to show my overlap. And notice how this is end-to-end overlap, because we are drawing a sigma bond. So this is the sp orbital overlapping with the other sp orbital. And then finally, I'm going to get my molecular orbital, my sigma bond or sigma orbital, which is going to have that little tail on one side, and then it's going to have an area of the combined orbitals together here. Now, it is generally a good idea, I'll just leave it at that. It is generally a good idea when you draw this to still show somewhat your nucleuses or some kind of reference. So I'm going to grab here, I'm going to draw my nuclei. Still going to draw it here. And then I'm going to draw them here. Essentially, that's the center of your atoms that are combining. You want to have some kind of indication of where they are. So here I have my step 1. Here I have my step 2. I have the orbital overlap. I have the actual molecular orbital that's created. And for good measure, it's very good to show your initial, because sometimes that's what they're looking for, not the overlap of the initial. And if we look at the mark scheme here, that's what they're looking for. They're looking for your initial sp hybrid orbitals, although they will probably have taken for this mark 1 the overlap that we show here, because it still shows the 2 individual orbitals, hybrid orbitals. And then they want to see your overlap of both hybrids becoming one molecular orbital of that sigma bond here. So 1 point for you showing either the 2 hybrids or the combination of the hybrids overlapping, or the drawing of the hybrids overlapping, and then 1 for showing the actually combined hybrids into one molecular orbital. All right. So there are various variations of these questions. Most of them are gonna pass you for one of these things, of course, when you're sketching either the overlap, the actual molecular orbital, or some combination of the process. All right. But you can figure them out as you read them. Just be very careful with the wording of the question. Well, that's it for this section. Thank you for joining us, and I'll see you in the next video.